Bhaskar sir, Ram will queue at sharp at 4 to begin the event. Sir, please switch on your audio as well now. You can do that.
Good afternoon to all participants who are joining for this webinar from India, and a very good morning to the participants from Canada. I request all of you to mute your audios and settle down as we are about to begin the webinar in the next few minutes. Thank you.
Sir, it's 4 o'clock. Colonel Bhaskar ji, you can start the session.
Okay. Good afternoon and good morning, everybody. I extend a very warm welcome to all the participants and our esteemed panel of experts at this third episode of the second season of the ongoing webinar series, Industrial Water and Effluent Treatment, IWET. This event is organized by the Smart Water and Waste World, which is a community engagement platform and brings together the world's water and waste communities through print, live events, training programs, and market solutions. I am Colonel Bhaskar Tatwavadi, a veteran and a water reclamation enthusiast. I am a director at Double Shots Private Limited, and I will be your host for this session. Coincidentally, I also hosted the first international webinar of 2021 for Smart Water and Waste World on the 12th of January 21 with water professionals and experts from the USA. Today, we are going to have some very highly engaging technical presentations, case studies, and question and answer sessions with our panel of water experts on some of the hottest topics of industrial water and effluent treatment plants, systems, technologies, and processes. I request all the members of the audience to send us your questions in the Q&A box in this Zoom application, and we will try and take as many questions as we can after each presentation, and probably time permitting, we shall have a Q&A session at the end, towards the end of this webinar. I shall begin this session by calling upon Ms. Annabelle Larouche for today's opening address. She is the Counsellor and Senior Trade Commissioner at Global Affairs Canada It's over to you, Ms. Annabelle.
Thank you very much, Colonel Bashkar. Good afternoon, everyone. First of all, I would like to thank Mr. Kailash Shirodkar and Smart Water and Wastewater World for partnering with Canada for this webinar series. Thank you very much as well to all of you for taking this time to join us today. It's great to have such a wide range of water and wastewater industry players attending this event. So I joined the Canadian High Commission in Delhi as the Senior Trade Commissioner in August, and I'm very pleased to support Canada-India commercial relationship and to be working in such a dynamic market. Just to give you an idea of the scale of the relationship, there are over 150 Canadian companies active in Western India and nearly 100 Indian companies established in Canada. When it comes to clean tech, Canada has an ambitious innovation agenda and has made clean technologies, including water and wastewater, a priority area. Canadian water and wastewater firms have a global reputation for excellence, and their groundbreaking technologies and solutions are addressing water challenges around the world. Close to 80% of Canadian water and wastewater companies are exporters, and their technologies and services are already being used in markets such as the US, Europe, South America, and Asia. And many of these companies are ready to further expand their presence in new markets. From conveyance to distribution to treatment and reuse, Canadian solutions are dramatically changing the way the world manages water and wastewater. Canadian technology also offers world-class technologies in a wide range of subsectors, including advanced disinfection and filtration technologies, biological and chemical treatments, pipe inspection, leak detection and infrastructure rehabilitation, resource and recovery and water reuse, real-time monitoring and water security tools, smart and digital decision support systems, stormwater management, energy efficient technology and optimized designs, and of course, consulting and engineering. And I would like to note that a number of Canadian companies are already present in India, ready to do business. So today you will be hearing from Medtech and their laboratory and portable analyzers for water, soil, and food. Of note, they have agents in the Indian market. Medtech has also supplied their analyzers to monitor the water quality of the river Ganga. You will also hear from Forward Water Technologies, who has developed a revolutionary product used in remediation of wastewater. And today they are joined by their Indian partner, Goldfinch Engineering. These companies are experts in their fields and offer unique solutions. During their presentation, they will provide deeper insights and models of collaboration and partnership. So this is the third event of the IWET series. And by the end of today's webinar, we would have had 6 Canadian companies who presented their state-of-the-art products and technologies on this platform. So please do connect with us and with the organizer to set up meetings with these great Canadian companies. Today, I'm with my colleague Yasmin Dubash, who is the Trade Commissioner for Clean Tech at the Canadian General Consulate in Mumbai. She's an experienced officer and looking forward to facilitate introduction and offer advice on how to engage with Canada. For those who don't know about the Trade Commissioner's Service, to which Yasmin and I belong, it's a key resource for Indian companies seeking to do business and source goods, services, and technologies from Canada, or to partner with Canadian firms. So we have a network of 8 trade offices and over 55 trade commissioners across India dedicated to advance trade and investment relations with India with a focus on Canadian exports, innovation partnership, and attracting Indian investment into Canada. I'm confident that this webinar will be a very good opportunity for you all to create new connections between Canadian and Indian companies. I really thank you very much for your participation. I wish you very productive discussion and thank you so much. Merci beaucoup. Over to you, Colonel Bashkar, sorry.
Thank you for those introductory remarks and sensitizing us to this wide spectrum of activities which have been undertaken by the water fraternity and the water companies from Canada. Thank you again. Next, I request Mr. Robert Meneghetto. He is the President and CEO of Medtech from Canada, and he will be presenting a case study on rapid and safe COD analyzer optimizing production at an industrial wastewater treatment facility. It's over to you, Robert.
Well, thank you, Colonel Bashkar. Thank you for that wonderful introduction. Annabelle, thank you, and everyone at the Trade Commission and IWET for this opportunity to present to this great group. Thank you very much. I believe this is very relevant. Water and wastewater, as I've said over the past 2 years, or let's say 21 months, no government wanted water problems on top of COVID, and it's really become even more important. And now with the accords regarding climate change, for example, we are seeing very significant carbon underlying themes in many discussions we're having just over the last 2 months even. And it comes into treatment, optimization, and data, which is monitoring and analysis. So I will start now. Thank you very much again. So who is Medtech? So we are, actually I like to say we're a developer and then commercialization and manufacture of laboratory online and portable analyzers for water, wastewater, and recently we've been moving into food and beverage analysis as well. Our mission, number one, is to provide quality results. If the results of the water testing provided by Medtech analyzers are not trusted, then we're out of business. So that's number one. Number two, we're going to do it in a way that is as fast as possible to generate those results than can ever be done before. And we're going to do it in a green way. We're going to do it with less reagents. We're going to have a green chemistry method. And we're also going to have a green impact because of the faster results. So if a candy factory, a dairy plant has their optimization of treatment, anaerobic digestion, or effluent control, they have those results minutes versus hours and days from the other currently established methods. That is already generating positive economic and sustainable impacts that protect the environment and protect public health. So we're 12 years old. We have 2,900 analyzers in more than 50 countries, excuse me. And we estimate more than 650,000 samples a day. So we're talking today about a company called Clean Harbors, which is it's a publicly traded company in the United States. They're located in both Canada and USA. Waste management company. So this particular site is treating trucked wastewater, industrial wastewater from other plants. So for example, it could be an automotive plant, which we have a lot of here near our area in, say, Toronto area. It could be auto parts, refineries, because we have refineries, chemical plant, dairy, beer, etc. So all of this different wastewater is coming to this plant. And 200,000 liters a day are treated and discharged to the sewer to go to the centralized treatment plant, the local wastewater treatment plant. So Clean Harbors itself is a centralized treatment plant for multiple industries, 200,000 liters a day. And they want to know the COD results, chemical oxygen demand, for the influent, so they can determine acceptance or refusal of that, because if it's too high strength, it needs to go to another plant. And then the permit for discharge is based on BOD, which is what North America typically does. And so they'd like to know what that is, because today, that is, because they only know from a regulatory point of view once every 30 days when they receive the invoice from the city, which does a random sampling 7 days of the month, and they average that over the month. So the inefficiencies that were identified were the COD analysis for the influent was approximately a 3-hour analysis time. Therefore, like, the trucks would unload in 1 hour. So they didn't know what it was. And sometimes they had to call the truck back because it was too high strength. And certainly we're not optimizing effectively because the wastewater is already in there. And of course, the standard method that's in the market for 60 plus years is dichromate or chromium based digestion. And it's not the greatest. In some cases, it could have been 5 hours out, because if you don't have all the samples within about 10 minutes collected, you have to wait for the entire 3 hours. When another truck came in, even maybe 10 minutes later, you'd have to wait 5 or 6 hours for that result, because it's a batch process. No effective analysis during the treatment, especially since they can get maximum in a working day 3 tests, 3 batches per day. And then the BOD was every 30 days. So it's unfeasible for them to do anything with that information other than wait for the invoice. So yeah, as you can see here, it's all unknown. So we developed, we manufacture. It is a patented device. Medtech owns this. It's a safe, green, true green chemistry, chemical oxygen demand analyzer. We're using nanotech. It's TiO2 oxidation. So when we explain this to engineers, we actually say this is a treatment technology. It is actually an advanced oxidation process. So it's treating the wastewater inside this unit. That's the first thing it's doing. And then so that technology of TiO2 treatment is actually being used already. For example, in Canada's oil sands to treat open to sunlight lagoons. TiO2 nanoparticles slowly, gently mixed through the lagoon, open to sunlight to activate it, will oxidize and clean up the lagoon. It's used, TiO2 used for treatment in Utah for drinking water. It's kind of interesting. I'm not exactly sure why that niche there, but that's what it is. Where we came in, we took this technology and we coupled it with electrochemistry to provide an analysis component. So that's why we call it PE, photoelectrochemistry. So it's safe, it's green. It's approximately 10 minutes to get the sample results. It's reliable. We're getting more or less the same values as the traditional COD method being used for over 60 years. And it's got a strong correlation to BOD as well, which has been quite a positive. So yeah, I explained the chemistry. There we go. So one thing we like to talk about is our collaboration with the University of Waterloo. So last year, we funded and opened a brand new lab at the Institute of Nanotech, or the Nano and Microsystems Lab at the University of Waterloo. They are manufacturing the slides and nanotech for us, but on top of that, already improving the technology and developing other analyzers with us for based on nanotech. So really excited by that. We're a year and a half in. We've committed to 3.5 more years already. And that's actually one of 4 funding collaborations that we have with Canadian universities, basically on water tech. So we talked about the operational efficiencies. Well, this is what happens now with the Peacock. It has happened, not what happened, has happened for Clean Harbors. They've got that 10-minute analysis time. That truck is still in the bay. They know what that COD is. They know if they have to put it back on the truck. They're optimizing immediately. And of note, if it's a low strength, it goes right to a holding tank. They don't have to wait. And what's really important to note, this is a mixed matrix. We don't know what's coming in on any day here. So it doesn't matter if it's dairy or refinery or automotive. The Peacock is an empirical analysis device standardized against a standard or calibrated, and it could just run, it gives you the correct empirical results back. There's no correlation back to a lab or you're worrying about matrix changes, anything like that, none of that. This is an empirical device, can grab it up, I can pick it up, go to another site, I just run the sample, I get a true COD result. So easily during analysis, of course, optimization. And what was really a real bonus for Clean Harbors, the exact same instrument with an algorithm, because that is correlated now to the BOD5 for their treated effluent. And the same unit every day it goes from COD to BOD. Here you go, whatever they need. And they know the discharge of their BOD every day. And it's simple. They've been using this now for 5 years. It's estimated that the additional profit for them per year since Peacock is roughly $500,000. This is the tool that runs their plant. They have my team come on site. I think it's twice a year for maintenance. They cannot afford to have this down. This is the tool once they got this tool. It is to run the plant. So it's a nice testimonial from the general manager there. So just, yeah, like I said, it's approximately $500,000 in savings. They are optimizing their treatment. They're using a ferric chloride treatment or biological. They have, I think, 6 or 8 different tanks. Some are chemical, some are biological. So there's energy and chemical usage optimization happening as well. Of course, eliminating that unnecessary transportation, which is costly, but now it's got an extra benefit on the carbon economy that's coming with carbon offsets. And as we deliver and we're bringing in more digitization tools, we're building in functionality like email alert functionality. You know, what does the data mean? Go to your phone, so they don't have to watch it. You know, even though it's unattended, they can set the sample and forget it. And they actually have an auto sampler as well, so they can, if 3 trucks came in, they can just load all 3 samples and walk away. The units are typically benchtop, safe, so anyone can use it, and simple. We don't install these. Basically, we send it out. There's videos in 60 minutes. An operator, an engineer, scientist is up and running. And then we've got portable. We have, for example, a graduate student running around up in Northern Ontario, measuring COD and now carbon, which I'll quickly talk about, right at the lakes at the International Institute of Sustainable Development at the Experimental Lakes area. So that's a huge impact from really a simple device that's community accessible. So in India, and Annabelle mentioned this, yeah, we're proud about our distributor with Swan Analytical and getting 5 Peacock Analyzers at different monitoring sites regarding the River Ganga. And basically what's really important here is traditionally around the world, TOC or total organic carbon, of course, is something that's measured. But a key thing that's been missing as an effective tool is called oxidizability, or the reactive fraction of TOC. And this little fraction, if you will, is becoming problematic with climate change. And it needs to be measured more effectively and not just at the lab level. And we have it. This is what this does. And so basically, it is helping to do that. And we're seeing impact for this both in Europe and even in Canada, where in Canada, the Health Canada has now added a new parameter to our drinking water guidance, which is related to reactivity. And of course, because Peacock is the only analyzer right now that can do that effectively, the Peacock method, if you will, has been referenced. And there is an international ASTM method now referencing the Peacock method. I think the other thing is a biogas that's coming up, of course, with climate change. And so we have the 2 tools necessary for that optimization. That is the COD, whether it's a very dirty sample, it doesn't matter. We know how to get it into the Peacock now without filtering. And then we also have the very important phosphates, so like volatile acidity and the basically free acids. So we make that as well. And we have all the software to make it one. It could be benchtop or it could be online, autonomous as well. And then something else that just happened last night, I'd like to announce. We submitted a proposal to the World Wildlife Foundation Challenge, WWF, regarding a community level accessible analyzer to measure carbon in nature, being water, biomass, and soil. I think it's roughly 310 submissions. We've been selected in the final 10. I will say that we're probably, I'm guessing, the only company or group, because I'm sure there's groups as well, that actually submitted data, not a concept. We already have, for example, carbon and soil applied to this analyzer, very simply as well. So I thank you very much for the opportunity again. We have 2 distributors in India, Fatki Instruments and Swan Environmental, and you have my contact information here as well. Thank you again.
Thank you, Robert, for that very nice presentation on the COD analyzers. Robert, there are a couple of questions for you. The first question is from Anthony Fernandez. He would like to know the references of your clients in the Middle East and in India? Of course, I heard about the Namami Gange project. Other than that, if you have any plants where these analyzers are being used, please enlighten us.
Yeah, like top of mind for me would be some Middle East places for sure. Like for example, one is the HID Power Company, which is a utility, right? So it's water, electricity, and that's in Bahrain. They're using Peacock actually mainly for stormwater monitoring. That's a big one. You can imagine as the storms are getting more and more frequent or bigger, what does a utility do with all this water effectively? You know, are they going to allow a whole bunch of, unfortunately, sewage go into the river untreated because it cannot be handled? So one thing is to effectively measure 24/7 or when you want, right, a COD or BOD. That really helps that decision that makes. That's one. But I'm happy to answer more about that offline as well.
Okay, the next question is from Prashant Kumar. He wants to know, is there any interference due to turbidity and suspended solids in the COD measurement?
Yeah, great question. There used to be about 4 months ago, not anymore. We've actually figured out a very simple sample prep method that gets the sample homogeneous, basically, no filtering required. And we take the sample straight up, right into the unit. So no interference, no.
Great. Thank you, Robert, for
Thank
those
you.
questions. Thank you.
Colonel Bhaskar, we invite you to make your presentation now.
Yes, I'm doing that.
Do you want me to share it for you?
Yeah, Ramkumar, if you could, please.
Okay. So the screen sharing is on.
Yeah.
Sir, do you want me to move to the next slide?
No, just a moment. So I start with my presentation, and my presentation is about troubleshooting in industrial wastewater treatment plants. Some common issues and how to fix them. Yeah, next one. Okay, so I will start with an overview of the Indian industries and touch upon the industrial wastewater treatment scenario, the concepts of ZLD and MLD, the problems encountered in wastewater treatment. Move on to the issues and attitudes when it comes to wastewater treatment. Data analysis, its importance, followed by troubleshooting, and I will conclude with some of my own reflections. Thank you. Next one. This is an overview of the Indian industries. The industrial output in India in 2020 was 340 billion US dollars, constituting about 13% of the GDP. This was expected to grow by 4% year on year in 2021. Indian exports during 2021 were about $292 billion. In addition, IT and IT-enabled services exports were about 134 billion US dollars. Very surprisingly, Canada does not feature in the top 20 trade partners of India. And we had a total trade of about 11 billion Canadian dollars in terms of imports and exports. When we talk about India's top exports, these are in gems and jewelry, minerals, petroleum products, auto and machinery, pharma, iron and steel, textiles, cotton, aluminum, meat and seafood, and cereals, and IT-enabled services, products and services. If we come to the number of micro, small, and medium enterprises in India, this number was 63.39 million in 2020. And in addition to this number, there were 700,000 large manufacturing units in India. The industrial sectors which constitute these units include battery manufacturing, petroleum and petrochemicals, chemicals and fertilizers, oil and gas, power plants, pulp and paper, food processing and beverages, textiles and apparels, iron and steel, construction and infrastructure, metals and fabrication, electronics and telecommunications, mining and quarrying, pharmaceuticals, nuclear industry, wood and timber processing, automobiles, plastics, gems and jewelry, and ITES. Next. Now, all these units, they contribute to the generation of industrial wastewater and industrial effluent. According to the Ministry of Water Resources, Government of India, about 40 billion cubic meters water out of the total available fresh water is used in industries every year. Out of this, about 10 billion cubic meters of water is used by the processing industries. About 30 billion cubic meters is used for power generation. The Central Pollution Control Board, or the CPCB, estimates that about 30 billion cubic meters of wastewater is generated annually. This translates into almost 82,200 million liters per day, or 82 billion liters per day. If we take a median cost of about 20 cents per kiloliter for the treatment of this effluent which is generated, the market size of effluent treatment in India is at least $6 billion per year. Next. Now I come to the industrial wastewater treatment. The treatment describes the processes which are used for reducing the pollution potential of the effluent produced by industries, which is an undesirable byproduct of the processes of the manufacturing. Most industries have their own facilities where they treat the wastewater so that the pollutant concentrations in the treated wastewater which is discharged, they comply with the regulations about disposal. whether the disposal is on land or in aquatic environment. Now, recent trends have been to minimize such production of wastewater or to treat the recycled waste, to treat the wastewater for recycle and reuse. That is the process of reclamation of water from wastewater. Many industries have been successful at redesigning their manufacturing processes with the intention to reduce or eliminate the pollutants. Next. Okay, the objectives of wastewater treatment broadly include the management of wastewater which is generated, or the management of brine if it is high in TDS, removal of solids, removal of oil and grease, removal of organics and reduction of the biodegradable matter, removal of other organics which are non-biodegradable, removal of acids, alkalis, toxic materials, lowering the temperature and reducing thermal pollution, sludge management, and safe discharge of the treated effluent in the ambient environment. Next. Now, zero liquid discharge, ZLD, regime for wastewater management, it requires that no liquid should go out of the factory premises. All the water that is brought into the factory should be consumed by the factory, and not a drop of water should go out. As against this, the minimum liquid discharge, or MLD, it aims to reduce the liquid discharge to the minimum. Now, while these concepts are ideal to reduce or eliminate the pollution potential of the treated effluent, in actual practice, ZLD is very, very rarely achieved. On the other hand, MLD can be a progressive target and it can be refined to optimum level. We must remember that both ZLD and MLD, they affect the bottom lines. Now the problems arise in the wastewater treatment plants because these plants, they receive material or liquids sometimes which they are not designed to handle, and many plants are either poorly specified, poorly designed, badly constructed, operated by default, and not maintained properly. What happens sometimes is that the manufacturing facilities or the main manufacturing plants, they increase production volumes. They also diversify the product line, but the plant owners, they do not upgrade the effluent treatment plant to handle the changes in the nature and the contents of the effluent. There are known events of dumping of chemicals, solvents, oils in wastewater, which the treatment plants are not designed to handle. Next. In addition to the problems, there are the issues and attitudes related to the operation and maintenance of the wastewater treatment plants. This results in high and variable rates of process failure. The operating staff is constantly searching for technical fixes for operation of the plant. Many times, control of the treatment plants is taken away from the operators. There are several theories about the causes of the problems. Sometimes there is a denial that there is a problem in the operation of plant. There is a long history of failed attempts to improve control, a long history of poor staffing. Energy consumption is a big issue, and the owners do not want a huge power bill. Unskilled staff and skilled staff shortage have been perennial in most of the wastewater treatment plants in the industrial sector. all of these affect the wastewater treatment. Now, the running of a wastewater treatment plant is into two parts. The first part is the system operation, which is a combination of several processes involving machinery, equipment. And second is the maintenance of the infrastructure, which involves regular upkeep and maintenance of the machinery, equipment, and the civil structures of the plant. Together, the system operation and maintenance, they lead to the treatment of the effluent in accordance with the legislation and which is enforceable by law. Now, troubleshooting has to take into account the aspects of system operation as well as maintenance. Now, basically, troubleshooting requires a lot of data about the plant, its operational history and maintenance records. So we begin with data analysis. When it comes to troubleshooting, the data available may be too little or too much, and in many cases, it may have to be regenerated in sufficient quantity for this purpose. When we, okay, coming to the, it's okay, we go to the next slide. Coming to the troubleshooting, I'm going to talk about the issues which are encountered generally in the wastewater treatment plants. If you want to avoid troubleshooting and you are contemplating a new wastewater treatment plant, my suggestion is that you should go for design, build, operate regime, where the plant designer designs, constructs, and operates the plant for a fixed duration with assured results. This is enforceable by law, and punitive damages can be imposed if the plant does not function. So that would avoid troubleshooting by the plant owner. However, for the existing plants, the problems start at the entry to the plant. For screening and equalization processes, the screens get stuck. The equalization processes do not operate optimally, and the remedies include continuous cleaning and removal of the solids, debris, mechanically or manually. And for equalization, a larger tank size, good ventilation, aeration, stirring and mixing can help a lot. Next. When it comes to biological processes, we find that most biological processes are disturbed due to shock loads. Shock loads could be by way of increased flow rates or by way of increased quantity of pollutants. These affect the culture growth and sustenance of the biological flora and fauna in the plant, which also gets affected due to pH, temperature, poor air or oxygen supply, poor equalization upstream, and changing variable toxicity of feed. The remedies include identification of the cause, readjustment of pH, longer hydraulic retention times for temperature control, monitoring and supply of DO and air, flow rate control, and toxic load control in accordance with the process design. Sufficient surface area for attached growth and sludge sloughing and removal efficiency using pulsators can also help in better functioning of the biological processes. Next. Next. As far as the mechanical equipment is concerned, the pumps, air compressors, air supply grids, mixing equipment, valves, and flotation devices, they all need to be maintained properly and operated efficiently. Use of variable frequency drives, adequate standby capacity, regular maintenance, periodic inspection for submerged parts, corrosion protection, desludging of dead pockets, spares in stock for pumps and compressors, and checking the inventories. In addition to the constant liaison with manufacturers of equipment for automation and control related issues can help in troubleshooting. In addition to this, if the plant is operating with sensors, the condition of sensors, their cleaning and the condition of cabling has to be regularly monitored. Next. Membrane processes are very important part of many wastewater treatment plant, starting from microfiltration, ultrafiltration, nanofiltration, reverse osmosis, and now also forward osmosis is also an option. All these processes, they use membranes. These membranes are made up of different types of materials. Their fouling, ruptures, clogging, and other operational problems, they affect the plant output. Among the remedies, I can mention regular cleaning in place as per the manufacturer's manuals, monitoring of SDI, that is the silt density index, before feeding RO trains must be done. Algal growth in the RO feed has to be eliminated. In membrane bioreactors and few other types of reactors, a pulse mechanism for shaking out or dislodging the biosolids, adequate stock of cleaning chemicals, choice of the material of construction of membranes, pH and temperature control and monitoring are very important, and these can help in troubleshooting the problems related to membrane processes. Next. There are several types of emissions which occur when organics and inorganics break down into oxidized solids, liquid rejects, and gases. Many times the wastes are consigned to pyrolysis and incineration. And if these processes are not monitored, gaseous emissions, which are toxic and harmful, are released into environment. Therefore, it is important to preheat these units before waste is consigned into them or injected into the chambers. Regular stocking, cleaning of residues, maintenance of metal parts, refractories, it must be carried out regularly. And this will help in reduction of emissions as well as proper functioning of the incinerators and pyrolysis units. Next. Yes, a very important aspect is the sludge management or the residual biosolids management. In the contemporary circular economy practices, the stress is on resource recovery, and due to process malfunctioning in bioreactors, there is an impact on sludge quality and its consistency gets affected. Among the remedies, the collection, dewatering, formation of mud cakes for the intended use has to be monitored regularly. Hazardous sludge must be handled with caution and properly segregated before final disposal. It is important to note that these sludges should not be generally sent to the landfills. Next. Considering the cross-section of the audience for today's webinar, I felt that this troubleshooting for the problems in industrial wastewater treatment plants as a general topic of discussion was a good beginning before a discussion on process units and specific treatment processes can happen. Now, troubleshooting is a deliberate and data-based drill. Every treatment process, every treatment plant, and every industry is unique in design, operation, and efficiency of treatment. And so are the solutions and remedies for these processes. the process and technology owners and vendors provide their operation and maintenance manuals to the owners. These are important and they merit serious implementation. Finally, our human experience of the plant operators, their skills and ingenuity of our engineers in tandem with the contemporary tools like Internet of Things and also aided by digital twins will ensure that these operations are not derailed and that the ETPs perform optimally with precision. Ladies and gentlemen, with that, I come to the end of my presentation. I will take up any questions which you may have. These are my contact details. Thank you very much.
Sir, request you to take up a few questions from the Q&A box.
Yes. There is a question from Dalip Chatwal about the removal of coliform. I would normally not encounter coliform in industrial wastewater. Coliform is generally associated with sewage, and normally the coliform removal happens through the biological process where the BOD and COD is removed. The last stage in coliform removal is the disinfection process, which can happen either with chlorination or with ozonation or through other sophisticated means like the UV radiation. A question from Anthony Fernandez. What methods are used to mitigate corrosion effects of the influent and effluent in wastewater treatment plants? To this, my answer is that most of the submerged parts of the wastewater treatment plants, which include the clarifiers, clarifying mechanism, these are normally epoxy coated. These days, many of the submerged parts are coated with a thin film of polyethylene or some similar material, and these can enhance the life of the submerged parts. Sugar, there is a question from Sudhir Kumar Singh. Sugar ETP treated water color is yellowish. What is the reason? Now, this yellowish color is the residual color which is left over after full treatment. After full treatment of the effluent. Color removal is one of the most difficult processes and most expensive processes. And there are permissible standards to which the color has to be removed before the effluent is discharged. However, complete color removal is neither economical nor practiced by the sugar factories. And there are measures available, but the best process available could be the membrane processes, which will remove the complete color. Unfortunately, those processes may not be employed by the sugar factories. Another question from Anthony Fernandez. What methods are available to address hazardous gases? Hazardous gases. Okay. Hazardous gases are hydrogen sulfide. Another hazardous gas is methane. And there are several methods available to collect the methane gas, and methane has to be disposed of. Normally, it can be in landfills. It can be collected and flared, which is what is done in many locations. However, in wastewater treatment plants, again, these gases can be collected and disposed of in accordance with the prescribed practices. Is there any? There is a question from Papula Nancy Samyukta about alternatives or replacements to pre-treatment screens. Screening is the first stage of treatment, and screens come in different sizes, shapes. So depending on the type of impurities that you expect in the effluent, you may position the coarse screens, the fine screens, finer screens, and even our other products which we use as filters of all types. These are nothing but screens in the true sense of the word. So you need to check your specific requirement, and you can get the answer from the screen manufacturers, which would be the best screen for your particular use. How do you go about solid disposal of solid screenings is a question from Samson Ibrahim. This would depend upon the nature of the solids. If those are inorganic solids and non-hazardous, these could be collected and disposed of in landfills. Process of remove. I think more questions can be answered subsequently.
Colonel Bhaskar, Robert has a question. I think we should take it up.
Robert.
Hello.
Yeah,
Yes,
hi, Robert.
Hi, sorry. I apologize. I noticed my hand was up. I don't know how I did that. And I just turned it off. But fantastic presentation. Thank you.
Robert, I think you received a few questions later on.
Yes, thank you.
After your presentation was over. So if you would like to answer a few of them here in detail, you can do that.
Oh, okay, sure. Yeah, thank you. There was quite a few questions. I think one was related to chlorine interference. Number one, there is no interference to chlorine with the Peacock technology, and it is photocatalysis, answering another question, photocatalytic oxidation. The interference is chloride, Cl-, and that is handled through our nanotech technology. Basically, we have a silver solid state with the nanotech sensor that takes care of the chloride interference to nullify it. So that is also taken care of. But very important to note, chlorine disinfection is not an interferent to the Peacock method, nor is color. And as mentioned with another question too, a TSS or turbidity, not an interference. In fact, brought into the analyzer, no pre-filtration required. I think I took care of 3 or 4 questions there.
Next, I will call upon Mr. Grant Thornley. He is the Vice President, Engineering Sales at Forward Water Technologies from Canada, and he will give us a brief on the next generation in forward osmosis. After his presentation, there will be a short informative video for the audience. It's over to you, Mr. Grant Thornley.
Great. Well, thank you very much, Colonel Bashar. Really enjoyed your presentation, very informative, and reminded me of my past years working in a wastewater treatment plant, good or bad, but very informative. Thank you. In kind of in the same, the venue or chorus as Colonel Bhaskar talked about is on wastewater treatment or management, and he alluded to ZLD, zero liquid discharge, as well as challenges in the wastewater for reuse and the complexity of it. At Forward Water Technologies, what we looked at is we've been working on, I'm going to say, the challenge of water reuse and the reuse of very difficult or challenging wastewaters in which to reuse back into industry or discharge back to the environment. So we've been working on that for the past 20 years in order to come up with a solution which is both viable on regulatory means as well as the economics. So I liken it to forward osmosis we put forward as the new water energy nexus, because the solution, the water treatment, does require energy, and what we're focused on is that the solution can't be worse than the problem itself. So as we were developing these technologies, we were constantly looking at that nexus, is that, well, does it make sense that we can do these treatments, but is it going to consume, excess energy, which would then correlate to a larger carbon footprint or CO2. If we did this particular technology for water reuse in challenging waters, would that lead to increased chemical consumptions in which to pre-treat or modify? In that case, that could introduce contaminants as well as other variables that can't be discharged. So that could be potentially worse. And the last one, of course, is that it needs to be economical. In order to be viable in today's industry, where you have increases in populations, an increase in manufacturing, which is that nexus of a water increase, it puts more and more demands on our water resources and stresses them to the point that it exceeds the hydrological cycles that typically replenish it. So we went out and we, again, after years and years of research, were able to come up with technologies that we feel that answers the age-long question: how do I reuse these challenging waters in a safe and sustainable fashion? So Forward Water Technologies, we're a publicly traded company. But what we've been able to do is we patented a thermolytic draw chemistry, and Santosh will elaborate on that, but we've patented a draw chemistry, which is quite unique and advanced. We have patented the draw regeneration process, and we utilize advanced membranes, semi-permeable. And it's the combination that you can have these developments in technologies and the advancements, but the real, I'm going to say, the challenge is the integration and the marriage of those technologies. So you get advancements in chemistries and material sciences. How do I leverage that, and how do I integrate and marry them together to a complete turnkey solution offering? And that's what took us the longest time, is how do we get the synergies between all these? And we've been able to produce a new system, we call it our next generation in forward osmosis technology, using semi-permeable membranes. And the result of that allows us to deliver a sustainable, safe, and viable economic solution to wastewaters that are very challenging. When I say challenging, I'll define that waters or brines that are over 20,000 ppm, whereas reverse osmosis, great technology, I'm going to say the gold standard for desalination. But once you start getting past 20,000 ppm, the osmotic pressure goes very high. And now you have to increase the pumping pressure or the energy requirements in order to get that. So as you continue to go up from 20 to 30 to 40, the energy consumption almost becomes exponential. So RO cannot be used in these challenging waters. And vis-a-vis the reason that we have been innovating to really address those challenging wastewaters from 30,000 all the way up to 280,000 ppm. And that's what we've been able to commercialize, deliver, and advance to the market space. So that being said, I'll turn it over to Santosh, and he can drill into the technology a bit more and give you a better explanation than I have given you right now.
Grant, before we proceed further, would you like us to open the presentation file? If you could spend a couple of minutes more with that.
Sure.
Then we will run the video.
Oh, okay. Great. So who is, sorry, here, can, you can, I'm sorry, you can see my screen, correct? Great. So who is Forward Water Technologies? First, our vision is to develop technologies that accelerates the transition of technologies in the adoption of technologies for a clean water sustainable environment. And as I've indicated, that we are a publicly traded company, manufacturing in Canada. We have spent numerous years and a lot of resources in patenting thermolytic forward osmosis draw chemistry, which is an advancement that we've stood on the shoulders of some, and we've also advanced it in other areas, but we've been able to produce a new draw chemistry, which is quite very unique within the industry. Coupled to that, we've patented a regeneration process for that, which is very unique. And in addition to that, we've also added advancements in the semi-permeable membranes. So we are a designer and manufacturer of turnkey forward osmosis water treatment systems. We operate globally with Goldfinch Engineering as our partner in India. And what we do is we take a very holistic approach to challenging waters for reuse under a water management umbrella. Oh, there we are. So I won't belabor this since a couple of people have already touched on this. But the current conditions of our water resources are, I'm going to say, they're quite challenging. Acquisition costs are increasing because of water scarcity, supply and demand curve. Water scarcity continues to impact operations, whether they have enough water or don't. Disposal, because more restrictions. Where am I going to get rid of this? If I can't dump it into a river anymore, then my costs are going to go up in order for disposal. And the last is with the manufacturing through just through the sheer process of manufacturing and picking up contaminants, the processed waters become contaminated. And now if it is discharged, then that compounds the whole issues with the resources. So to sum it up is that those are the challenges, but there's also demands. We have increasing populations worldwide, which means that you also have to feed that population. And I'm going to say 60–70% of all water resources are associated to agriculture production. And of course, increased manufacturing. So we had these challenges, but we also have these increasing demands within the resources. So the solutions quite simply are, we got to reuse what we have on the wastewater. What we do discharge, it has to meet requirements. So for the public health and safety, but also for the environment itself, the legacy that we leave behind for our children. And lastly, we need to take more of an holistic approach to total water management, from entering the plant to exiting the plant. And if we were to take that, again, I'm stating a quite a simple approach to it, but that's what we need to do. But how do we get there? Next slide, please. Oh. It is, as I've indicated, is that years and years of R&D and resources have allocated. We've been able to work on 3 tiers of forward osmosis, which is the membrane, draw solution, and regeneration. And through chemistries and material sciences, we've been able to produce an advanced membrane. Coupled to that is we've been able to develop through chemistries, develop an advanced draw solution, and then lastly, through best practices and processes, advanced regeneration. So one company can work on this, but the real power of Forward Water Technologies was our ability to develop and then integrate all these technologies together into a single system, which is our forward osmosis system. And by doing that, we've been able to produce a very economical system that utilizes forward osmosis, which is free energy for extracting pure water from wastewater, challenging waters from 40,000 ppm all the way to 280,000 ppm, which are difficult, which would eliminate reverse osmosis as a solution, but may lead to other higher energy consuming, which is EVAPs and crystallizers. And we've been able to find a segment of utilizing, leveraging the technologies to place forward osmosis between RO and between a crystallizer, and being able to replace a lot of the technologies with a smaller footprint at lower CapEx and OpEx costs. So it makes it more viable and economical for people to retrofit or upgrade their plants. So I'll hand that over to Santosh. Thank you.
Thank you, Grant. Ram, if we can run the video on forward osmosis.
Fresh water. The supply is dwindling, yet industries need more of it. Heavily contaminated, untreatable wastewater must be burned with other waste, buried, or boiled. But the challenge of reducing waste streams can cost an individual company tens of thousands of dollars in energy, transportation, and disposal each year. Forward Water is addressing that challenge. Its proprietary forward osmosis process affordably extracts pure water that is no longer lost, and it reduces greenhouse gas output up to 40% compared to current disposal methods. At the same time, it reclaims clean water that, like a tool or machine, can be reused over and over. It also ensures compliance with water reclamation mandates. How does the three-step process work? Step 1, it starts with forward osmosis. This is where only water is spontaneously driven across a membrane. The water is attracted by a highly concentrated draw solution on the other side of the membrane, while the membrane blocks contaminants from passing through. Step 2, conversion. The diluted draw solute is converted into two gases. This is done using a combination of heat, reduced pressure, and a sweep gas that increases the flow. Once the gases are removed, only fresh water is left behind. Step 3, regeneration. The evolved gases are recycled to generate a fresh, highly concentrated draw solution and leaves behind fresh, clean water. Using the forward osmosis method, water may be cycled repeatedly in a closed-loop process. There are no chemical consumables and no secondary waste stream. Reclaiming water from the waste stream for reuse in the manufacturing plant means significant cost savings, both from less fresh water used and less waste to be disposed of. And the heat required for the draw solute conversion? It is compatible with low-grade industrial waste heat or solar thermal heat for further savings. Forward Technologies is changing the way industry handles wastewater. In India, please contact Goldfinch Engineering at 91 982 00 10509 for commercial forward osmosis systems.
Thank you for that video presentation. I will now request Mr. Santosh Bhide, who is the Director of Business Development at Goldfinch Engineering, which is the Indian partner of Forward Water Technologies from Canada. And his topic of presentation is Forward Osmosis, its potential realized. It's over to you, Santosh.
Yeah, good evening all. Thank you, Colonel. Let me share my screen. Yeah. So thank you, Grant. He gave a very good primer on the forward osmosis and what is the intention on the innovation and how we are going about it. In the next few slides, I will try to break it down into simplify into what is the real working of that from applicator point of view and how both ends are integrated to give a cost-effective water reclamation or low energy water reclamation solution. So as we know, there are many types of industries. Some I have listed here. Each industry has a different type of problem in terms of wastewater generation. Some are high volume, some are low volume but concentrated. Some will be having high organic contaminants, some will have high inorganic salts, some will have both together, which make it even tougher. So as mentioned in the previous presentation also, even by Colonel Bhaskar, that ZLD, now that has become a driver for wastewater treatment, and many state boards in India are increasingly specifying industry as a statutory compliance to recycle the treated wastewater for their own processes. Now, especially when the brines are having like TDS concentration is about 2% or 20,000 ppm, it gets very challenging. And if it also has organic contamination, that means the wastewater is not priorly biodegradable and some COD is left out along with the TDS, it becomes even more challenging because the conventional membrane process available are prone to fouling. In addition, it gets very energy intensive process because whenever you use either membranes or you go for evaporation or incineration, these are all very energy intensive processes. So can we have a process which mitigates some of the challenges? So that is what we are trying to bring here. So forward osmosis has a low fouling propensity, so that potential of fouling the membrane is very less. Even if we are putting through organic contaminated high TDS wastewater through the membrane, we can survive, we can recover the membrane and we can achieve the target. The rejection rate of this membrane is as good as reverse osmosis membrane. It is similar, I would say. And it has got a benefit of lower energy consumption. Why? That I will come to in the next slide. So all this gives some tangible benefits like it reduces the volume, a less footprint is required, it is less energy intensive, so it ultimately results in lower OPEX and COPEX also. So all these benefits, how we can achieve. First, let me explain briefly on what is forward osmosis. So probably some of the audience who may not have known about forward osmosis may be wondering a term which came up frequently in Grant's talk was a draw. So what is a draw solution? So first, let me take your attention to the right-hand side of this slide. So this is a process which is naturally occurring in all living organisms. It is a natural process. So it is copied from nature. So one example that is the mangroves. So mangroves are always in a saline water, and in spite of that, they are able to extract water from the saline environment around them. How that is possible? Because they generate a sugar solution inside the root, which is having even higher osmotic pressure than the surroundings, which is the saline water. And that is why through a protein which is present in all the living organisms, which is a water carrier, due to the osmotic gradient, water, exclusively the water flows inside the roots. So this process is aided by the aquaporin protein, and which is synthetically immobilized on the forward osmosis membrane. So that is the heart of the technology. So we call this membrane as a biomimetic membrane, which is like copied from nature. Now come to the left-hand side, where the blue sheet is a semi-permeable membrane. Now most of people know this is how we represent the membrane processes. And on the left-hand side, there are many red dots and blue dots which represents the polluted water. Now here it is written as valuables, nutrients, and aromas. But for this presentation, let us consider that as pollutants, maybe organic, inorganic, whatever. So on the left-hand side of the membrane is a feed solution, which is the contaminated water. And on the right-hand side is the draw solution. which is a solution which is having higher osmotic pressure than the feed solution. In simple terms, the draw solution is having higher TDS than the feed solution. So due to this osmotic gradient, as I explained, using the aquaporin layer, the water flows across the membrane. Only the water exclusively flows across the membrane. And the pollutants are retained on this side, concentrating the feed. So this is the principle of forward osmosis. So the analogy, like in a heat exchanger, everybody is aware there is a heat exchange between two fluids through the heat exchanger. So the hot one becomes cold and vice versa. So this forward osmosis is a water exchanger process. So on the top, I have put a picture of the membrane of forward osmosis membrane, which is a hollow fiber membrane. And due to the osmotic gradient, the water flows across the membrane. Now, comparing to reverse osmosis is a pressure-driven process. So, in proportionate with the TDS of the feed, we require higher and higher pump pressure. So, like high pressure pump is a very common term when we talk of reverse osmosis, and the pump pressure goes into 20, 30, 40 bar, depending on what is the TDS concentration. So, in the forward osmosis, it is not a pressure-driven process. So, whatever is the TDS concentration, I just need pressure of not more than 1 bar to circulate the water through my membrane. On the lumen side, the feed, and on the shell side, the draw solution, which affects the exchange of water across the membrane. So that is the difference between reverse osmosis and forward osmosis. And as you noted, because we are not pressing the solvents with high pressure across the membrane, the process is a very low falling process. We are not pushing the solvents into the membrane, unlike reverse osmosis. Now, to make this loop complete, we understood that we have got a draw solution, we have got a feed solution, and we have got a membrane. And across the membrane, the water is flowing due to the osmotic gradient. To make this process sustainable, we have to continuously, now if you see here, in the middle portion where the white arrows are put, is a semi-permeable membrane. The FO membrane is represented here. The feed is going in, and the draw solution is circulated on the shell side or the outside of the membrane. And due to that, the water is flowing. The white arrows is nothing but water flowing through, which is entering into the draw solution. And as a result, the feed is coming out concentrated. Now, whatever water has traveled across the membrane due to the osmotic gradient has made this draw, whatever draw I was using, dilute draw. So it will not have the same TDS concentration or the same osmotic pressure. So that is why this black box, which is a recovery system, is very important. Within the recovery system, we have to take out the water. So again, my draw tank receives the same draw which was required to cause the osmotic gradient across the membrane. So this explains why we need to regenerate the draw solution. And this is the key in making success of the forward osmosis systems. Because now suppose we use a normal saturated salt solution or a sodium chloride solution as a draw. Now what is happening? I will be able to generate the osmotic gradient. That sodium chloride solution will get diluted. Now to recover that draw and bring it back to its concentration, I may have to use again another membrane process like a seawater membrane or a nanofiltration or something. So my advantage of saving energy on the feed side is totally lost, and I have got again limitation because I cannot handle above a particular range of dissolved solids within the recovery system because of the limitation of the RO or NF systems. If I go for thermal evaporation, then the energy is very, very high, making the overall system unfeasible or uneconomical. So that is why generally in wastewater treatment, a free draw solution is not available, and we need to look into the draw. So this is the innovation that forward water technologies has brought, and which we are trying to integrate in the overall ZLD solutions. It has got 3 components. Of course, one is the heart of the technologies or the process is the semi-permeable membrane, which is available. Second is the draw solution, and third is regeneration of the draw solution. So how we go about it? So Water Technologies has come out with a proprietary water solvent salt, which is switchable. By switchable, what we means at certain temperature it switches. So it goes from polar to non-polar. So water is the most polar solvent, and we can dissolve it, generating very high osmotic pressure in one absorber column, I would say, which generates the high osmotic pressure, which facilitates my draw. And on applying some low heat, which is not high heat, I'm not boiling the water. So we can again dissociate the draw into the two compounds, which come out very easily to go back in the absorption. So this basically, with this process, we can generate a very high osmotic pressure. So as good as 215 atmosphere pressure can be generated, which is equivalent to 4.4 molar sodium chloride solution, I would say. So that one challenge is overcome, that I have got to draw which can facilitate a very high osmotic pressure. So even high feed TDS solutions are feasible to concentrate further. Now, energy requirement is less because it dissociates easily into two compounds at a low energy. And that causes a 100% closed loop system. And I'm not externally adding any salt in the system, but I'm generating the osmotic pressure with this proprietary switchable solvent salt. The reverse salt flux is very minimal or almost not there. So draw solution does not go to the feed side or the lumen side of the membrane. This is especially important if we are trying to concentrate some valuable stream in the process also. So how the process overall will work is, now on the left hand side, you can see a semi-permeable membrane. There is a feed input, there is a concentrated output, as I explained before. Here is a concentrated draw, which is coming from our proprietary switchable solute, which is mixed in this column, which generates the required osmotic gradient across the membrane, facilitating the water to travel across the membrane while concentrating the feed. As a result, this draw has become dilute, so we call it DDS or diluted draw solution, which goes back to another column here, where a low heat is applied and easily dissociating those proprietary chemicals which go back into the absorber. And the bottom of this column is a water. It is the same water which has traveled across the membrane, mixed in the draw, and come out from the bottom of the this column, which is the reclaimed water, or in the normal membrane terminology, I would say it is a permeate, I would say. So that is how the water is recovered with a low energy using forward osmosis membrane and the proprietary or innovative draw technology, which is developed by the forward water technologies. So FWT can give such a plant. This is a schematic skid basically, so which consists of, maybe these are the feed tanks, and this skid can be seen as a forward osmosis skid, and then there is a draw regeneration, a column type of thing which you can see, and there is a this process can be totally controlled using the PLC. So we can go concentration as explained by Grant up to 28% is the potential. Of course, we have to review what other peeling or scale forming or precipitating chemicals are present in the water, and we have to ensure the feasibility before we go for this. We can achieve a good flux. The operating temperature is also not very high. We can go for modular design, and we can retrofit, upgrade the capacity very easily, and we get very high solute rejection. Now the permeate or the recovered water from this is very good for secondary use, which we found from our actual operating data, and we can as an option give a polishing treatment to achieve less than 10 ppm TDS or whatever required for the reuse. This is one case study which Water Tech did within Canada. This uses different, very difficult oil and gas waste streams, which they were able to concentrate up to 85% in spite of the nature of the high fouling properties of the wastewater streams. So that has been done by them in Canada. I will talk specific about one case study which we have done in India. This is a plant which we have built and set up in India, in Maharashtra actually. And this is for a specialty chemical manufacturing unit. And we have operated it since last a few months. What is the data? So due to the product mix and the product campaigns, we fortunately could get different type of waste streams. Like I call it a lean stream, mixed stream, and concentrated stream. But the lean stream itself is like having 2% TDS. So this plant is about 10 KLD capacity. When it was a lean stream, I purposely put the COD also. So along with the dissolved solids, there was a COD of not less but 16,000 ppm, which also got concentrated. When we concentrated this through the membrane to 80%, that means we recovered 8 meter cube water out of the 10 meter cube. That means 80% recovery in a way. So in spite of the high COD, we could do that. And the membrane got recovered just by lumen wash. Okay. Similarly, when we are talking of mixed stream, which is having 5% TDS, we could concentrate up to 15% TDS in spite of the COD present in that. And when we are at a very high, like a concentrated stream, almost 15%, 14.5% at least dissolved solids in that, and also higher COD of 30,000 ppm, we could go up to 20% concentration of this stream. So causing about 23% recovery in the past, which is also good enough when we consider the evaporation energy required. So the electrical load and steam I have written here, but for such a small pilot plant, basically some minimum kilowatts are required. So I have extrapolated these results. Based on these results, a few cases where we have got a standardized design like 100 meter cube per day of feed to the plant, and dissolved solids concentration varying from 2%, 3%, 4%, 5%, and 6%. And I have just placed it so we can go up to 20%. I have just considered that we go up to say 15% concentration. So when is the feed concentration is less, I am achieving highest concentration or the recovery, which is 87%. And even for the highest TDS concentration of 6%, I am achieving a 60% recovery. Now you come to the utility required for the system as a whole, which consists of FO unit as well as the draw recovery unit. So if you note the electrical load in each case, as well as the steam, and which I have compared with the 4-effect evaporator. Now note again that when I consider the 4-effect evaporator, I have considered the volume of water recovered only, because in evaporator, whatever we are putting, the water will basically evaporate and we collect the condensate, which I am considering as permeate. So it is a sort of a apple-to-apple comparison when the volumes are considered. So even though this is done, you see the electrical load is ranging from 14% to 36% only of the evaporator. And the steam requirement is just 30% to say 70%, I would say 68%. So there is an energy saving, sorry, of a wide range. If your TDS is like 2 or 3%, like you're saving 60% energy or the steam requirement or the heating. Because I said we are not evaporating the water, we are just dissociating the draw. And when we have got even high TDS, still it is workable because we are able to save 30% of energy. Now, what are the opportunities where we can place the forward osmosis system? It is a customized thing, and we need to review the detailed analysis. Even if you have got existing plants, we can customize, we can retrofit the plant by placing the FO strategically at some point. So the top block
is the conventional process block, which consists of primary, secondary, tertiary treatment in the ETP, followed by RO, where we are concentrating in the RO, recovering some permeate, and the concentrate or reject of RO goes to evaporator ultimately when it is a ZLD. So I can replace the entire plant after the primary treatment by just putting FO. Or after the biological treatment, where I remove all the organic pollutants, which is the most environment friendly way of doing biologically, I can place the FO, replacing everything else and go to the desired concentration. Or I can even concentrate the reject of reverse osmosis further. So my feed to evaporator quantity is reduced, and mind well, per meter cube of feed water going to evaporator, I am saving in Indian rupees like 800 to 1000 rupees, if not less. So imagine the huge cost benefit here. Suppose you have got the operating plant and the wastewater volume is increasing, you can retrofit maybe the primary, secondary, tertiary systems, even probably the reverse osmosis, but you can avoid expanding on the evaporator by just placing the forward osmosis there to go back to the original design volume of ME by concentrating it further and recovering some water in the permeate. So this is, of course, we need to do a detailed evaluation before we recommend any of this. So Goldfinch has a facility to do this feasibility evaluation. We have got the pilot plants, manufacturing facility, and a state-of-art lab where we can do this. Of course, we are in the field since 3 decades in India, doing wastewater treatment and ZLD plants. So we have got a lot of exposure and experience on different type of wastewater streams. So we shall be easily able to do the lab proofing study as well as on-site pilot study and scale up to the commercial level, the forward osmosis solution to effect lower capex, lower opex, and of course the lower carbon footprint because the low energy is there. So this is all. Thank you very much.
Thank you, Mr. Santosh, for that presentation. I think your forward osmosis is a very interesting process, and many of us are looking forward to your responses to some of these questions which have been, coming thick and fast. The first question from Kondal Rao is the forward osmosis process applicable for municipal wastewater treatment?
Yeah, it is feasible, but considering the cost economics, I would place it for more of industrial wastewater treatment where the TDS concentration is high, like at least 15,000 ppm or more. That would be the sweet spot of this technology, because sewage will normally have a low TDS. So commercially, it may not really be worthwhile to do it.
In which case, brackish water RO membranes would be best suited, do you think?
Yeah, that is also possible, because sewage is very easily treatable first. So we remove all organics there at a low operating cost, I mean. And then once that is done, if you have got a TDS of 1000 ppm or so, we can of course do it through FO also. But then the RO would be a simpler and straightforward process for such simple applications. We are looking at more complex opportunities, basically.
Right. I have a question to you. Where do you see the forward osmosis technology? Is it likely to ever replace reverse osmosis and other membrane processes like nano filtration, ultrafiltration, or is this going to be only applicable for difficult industrial effluents?
I would definitely say this is not the replacement of RO or NF that has got its own application zone, but this will complement those membrane processes as well in many places. And some places where the technical feasibility is difficult for RO or NF because of high organic contamination as well as high TDS, then FO will come into play, because I myself have experience that I put in something like 1 lakh ppm COD through the FO membrane along with ITDS, and we could achieve the permeate recovery without fouling the membrane. So that has a different placement, and it is complementary and customized along with the other membrane processes.
If I can just add is reverse osmosis is the gold standard in desalination, to the point that the kinetics of it are almost mathematically equal, meaning that it's about 1.1 kilowatt hour per cubic meter of treatment. And on desal, I mean, as you increase the TDS level, as you're aware, the osmotic pressure goes up, which means that the pressure needs to be driven up higher and higher and higher, to the point that when you get up to about 30, I'm going to say max, very, very high pressures at 40,000 ppm, because you're driving so much pressure now, you can also start you're now compressing the membrane itself. So there's a limitation on the pressure, the integrity of the membrane itself, to how high you can drive that pressure up. Now, where can it be applied? Is FO can be applied as a pre-treatment to an RO to reduce the BODs, CODs, the fouling components to it, to allow the RO to run at a higher efficiency. And also through regulations is that you can also use the FO on the back end if regulations require the management of the brine. A lot of companies or municipalities now are being required, particularly in North America, you can't discharge the brine. You have to go through a ZLD process. So for municipalities, there's a potential for FO to be used in RO applications, but it really depends on the economics and the application itself.
Thank you, Grant. I have another question, and that is about the forward osmosis process is concentrating both COD and TDS. Am I correct?
Yes. In any membrane process, basically we are concentrating whatever is put in. It is not a selective concentration. Yeah.
True. Yet RO is generally not used for COD reduction.
Yeah, because organic fouling causes the transmembrane pressure to increase over a period and can cause failure of the membrane.
So the wastewater, which has a high COD, the COD reduction is generally done using activated carbon by adsorption or some other process. What is the comparison of the cost comparison for reduction of COD at say medium or moderate levels of say 1,000 to 2,000 milligrams per liter?
Well, it again depends. Activated carbon may sometimes work, may not work. It depends upon what organics you are having and the cost of adsorption on carbon, and then it generates a solid waste again, and the regeneration cost of that, everything is multiples. And it does become very problematic for the operator. If the plant is in MLDs, then the handling of that much carbon, recharging and removing, all becomes very difficult. So this will offer a simpler solution. If 1,000 to 2,000 ppm COD is not a challenge for us, we can definitely pass it through membrane. It will get, depending upon TDS, it will get concentrated. And ultimately, if the ZLD is the driver, then we'll do that. And if the COD is non-biodegradable or non-treatable by simpler means or low-cost means, then only we come into picture, all the membranes come into picture normally.
Okay, there is a question. What is the largest size of the forward osmosis plant installed so far, anywhere in the world?
Well, so far, yeah, Grant, please.
Currently we have a system in Canada where we're located out in Alberta in oil processing. So it's 15 cubic meters, but we have designs right now up to 1 million gallons a day. Of course, every application we need to go through mathematical modeling, through testing to validate designs, but we have designs and in process right now, up to about 38 cubic meters a day, and designs up to 1 million gallons a day.
Grant, other things being equal, that is the parameters being similar, what would be the price difference for a 1 MLD or a 1 MGD plant using reverse osmosis and using forward osmosis?
A challenging question with respect to, because when we take a look at the market segments, is we are operating in parameters in a range really outside the operations of an RO, meaning Colonel Bashar, is when you get into around 30 to 40,000 ppm TDS, the energy consumption again becomes exponential with an RO, but even at 40,000 ppm, it is outside the operating range of an RO system, even at high pressures. So that's where we're coming in, is saying, well, look, we can address the inefficiencies of RO and the exorbitant costs of evaporators, and that's kind of where our sweet spot is operating just above an RO with the ability to replace an evaporator within multiple processes within industry. So hopefully that answers, hopefully it's not too cryptic, but the RO, there's limitations, and the limitations of an RO, that's where we come into play. So we don't really play within the RO market, as I indicated previously, that we could put an FO in front of an RO or behind it for brine management or RO pre-treatment. But there are other technologies that can do that. Where our sweet spot is that when you get into these really, really challenging wastewaters, which have high fouling propensity, that other technologies are pushed to their limits. Our technologies allows a more viable economics because we're using the free available energy of osmosis, which is not a pressure driven or energy driven, and then separated using a salt draw solution with slight heat in order to separate the pure water from the draw, and then it's a closed loop to reprocess. So that's kind of where we play within the industry, is between an RO and an evaporator, if that makes sense.
Thank you. Another question. What are the requirements of the maintenance and cleaning of the membranes, and how difficult or how tedious these processes could be?
I'm sorry, Sash, you want me to take that, or do you?
Yeah, Grant, you can take that. Basically, it is asking about the CIP.
Right. So so we're a semi-permeable membrane. So the process is a solution diffusion across the membrane, unlike your previous discussion, Colonel Bakar, is through MF, microfiltration or ultrafiltration. And so if you say MF, UF, and RO, those are all pressure-driven systems. So you are applying, even though UF is a vacuum, that's still considered a pressure system. So you're creating, you're driving the solutes or the solids against the membrane and creating a polarization against the membrane, and you're also pushing those solids past the active membrane and into the membrane. So a conventional membrane system, because it's pressure driven, fouls because of the compression of the cake. So therefore the maintenance and operational costs are very high, as well as a unique regime of cleaning chemistries. On the contrast of forward osmosis, because we're using osmotic gradient, we're pulling or diffusing liquid across the membrane very gently. So the big difference here is that because you're not pressure driving the solids and compressing it, you're drawing, you don't have that polarization of solids on the surface. You don't have the compaction of the surface. So therefore, the cleaning of the membrane is quite simply increasing at a certain frequency, let's say 48 hours, is you increase the cross flow across the membrane to increase the turbulence, and that's how you clean it. And the difference is that with an FO is that you have recoverable flux, typically 99% recoverable, versus a pressure-driven system where you have irreversible flux recovery. So that is a huge difference between ours on the operating cost, the cleaning regime, but also when you get into the life cycle of the membrane itself, as you're probably aware, is that the more you clean a membrane, the more you take life away from it. So that's another big difference for ourselves, because we don't have the fouling propensity of a pressure-driven system. We get a higher production runtime. We get a lower cost of maintenance or cleaning. And we have, because it's a solution diffusion through a semi-permeable, permeate that's coming out at around 100 ppm TD, from 100, let's say, to 300 ppm TDS. So extremely pure permeate out of the system. So hopefully that answers your system. So the operating costs are, for cleaning is very low, because it is not a pressure-driven system. That's the main one. You don't compact those solids, and huge problem in pressure-driven membrane systems.
Thank you. Have there been any experiments at all on seawater forward osmosis to convert it into drinking water?
There has been several installations worldwide, not just ourselves, because FO is a tight community, and we work together to advance it. Excuse me. There's some areas for desalination where they're actually using an FORO, forward osmosis, reverse osmosis, for desalination. One of those areas is development is in Hawaii. And the unique, as Santosh has alluded to, is that you can use, if you have a draw, an available draw, which is the seawater, I can now use that as my draw solution. And depending on the geographic location, another aspect, when you use a regeneration of a draw, you can use solar energy. So in Hawaii or even India, because it's a low-grade heat, I can actually use thermal solar energy in which to drive the thermal component of the regeneration process. So we're finding more and more opportunities, particularly in warmer climates on coastal areas, where FORO is coming into play because of the synergy in the economics of it.
Thank you. One more question. Is there any pre-treatment requirement before the effluent or the wastewater or the water is fed to your forward osmosis membranes?
Yes, because as Santosh has indicated, it's a hollow fiber. It's around 0.2 millimeters inside diameter of the bore. So it is a relatively small bore. So therefore require around a 50 micron filter to take the solids out. So 50 to 100 microns, and it's an inside out configuration, meaning the wastewater is flowing through the center, and we have a draw on the outside of the hollow fiber. So we are looking at, just so you're aware, because whenever you have filtration, you also get a pressure drop, a delta across that, and that can be correlated to operating costs for pumps efficiency. So we are looking at increasing the diameter. So that will allow us to have if I can classify, a rougher filter. But currently it's a 50 micron. In about a year, 2 years, we'll be able to increase that, because we'll increase the bore diameter of the hollow fiber.
Yeah, still Grant, it is only microfiltration, unlike RO, which will require ultrafiltration. So the big difference between 0.03 or 0.04 micron and 50 micron. So the pressure is as such very less.
Yes, good point, very much.
Okay, just one more question. How do you handle the reject in the forward osmosis technology?
There is,
Sorry, you can take it. Sorry, Santosh, you can take it.
no,
I would
conventionally,
say, should I say concentrate?
yeah. See, basically we are placing forward osmosis in a ZLD plant. So
Right.
normally the RO reject, or if not RO reject, it has got high TDS as such and high organic pollutants. It is going to the evaporator. So we are reducing the volume which is going to the evaporation. So the concentrate will go to ultimately the evaporation, but the evaporation volumes are brought down like anything. Suppose like I have got a case study actually done where we have reduced it by 50 or 60%. So imagine the OPEX saved in his evaporation costs.
Are there any brands of the manufacturers of forward osmosis membranes?
The unique thing about, as I alluded to before in Santosh, is that there's three components or main components to a forward osmosis system. One is, of course, the membranes, the draw solution, and the recovery. The uniqueness of the system is that you can use different membranes, but it doesn't change the draw and the recovery. Now, different types of membranes mean different permeabilities or water solubilities. So you can use different membranes from different manufacturers within the system. So on a supply chain, you're not limited. That being said, we prefer to stick to one because it helps us with our design and configurations. But it doesn't mean that you could not use someone else's membrane.
Thank you, Grant. Thank you, Mr. Santosh. That was a very nice presentation, and yes, very insightful answers to the questions which were there from the audience and from my side. Thank you, gentlemen. Thank you very much.
Thanks, Santosh. Great presentation from across the pond.
Thank you.
Now, ladies and gentlemen, before we close today's episode 3 of IWET season 2, I would like to thank the IWET country partner Canada and both the technology partners Medtech and Forward Water Technologies for their support in conducting this webinar. My thanks are due to Miss Annabelle, Miss Yasmin, Robert, Grant, Santosh, all the participants of this webinar, and the attendees who were present in large number. And for their information, I would like to add that those who are interested in connecting with these Canadian companies and also want to explore business opportunities and want to learn more about the Canadian capabilities in the areas of water and wastewater treatment and management, the relevant contact details will be shown on the screen. Now you can approach them. Thank you all again for joining us today. IWET Smart Water and Waste World thanks all of you, with the promise to meet again next month in the episode 4 of this ongoing IWET webinar series, and your screen will show the contact details of these organizations, as I told you. Thank you, ladies and gentlemen. Have a great evening and a great day in Canada. Thank you.